Welcome back, everybody. In this video, we will explore the relationship between the equilibrium constant in terms of pressure and the equilibrium constant in terms of concentration. So let's talk about pressure. For gaseous reactions, the partial pressure of a particular gas is proportional to its concentration. And you can express equilibrium constants in terms of partial pressures. So always be mindful when you're working problems if it's asking for the equilibrium constant expression in terms of pressure or in terms of concentration. And the way we represent that is for concentration, Kc, and then pressure is Kp. Now, in later chapters, we'll cover Ka for weak acid equilibria, Kb for weak base equilibria, Ksp, which is solubility product equilibria, and Kf for complex ion equilibria, and all of these will be working in terms of concentration. So for the most part, you're using Kc, if you will. However, it is good to know how to do Kp if you are working with a gaseous reaction. Alright, so let's say you had this problem and you were asked to write the equilibrium constant expression in terms of partial pressures. So Kp is equal to what? Anytime you do equilibrium constant, it's always what over what? Fantastic. Products over reactants. Good. But in this case, you need to represent that as a partial pressure as opposed to in terms of molarity. So the partial pressure of sulfur dioxide to the second power times the partial pressure of oxygen, those are your products, over the partial pressure of sulfur trioxide to the second power there. Now, something to make note of, and there's going to be a reason why I'm doing this derivation for you, is that Kp is not necessarily equal to Kc. So let's talk about this. Let's do a derivation so we have a better understanding. So let's say hypothetically we have a substance A. Well, we know that the molarity or the concentration of A is equal to what over what? All right, moles over liters, but I'll just represent that as volume, right? Moles over the volume. And back in Chem 1A, you would have learned the ideal gas law. And what was the ideal gas law? Pivner, right? PV equals nRT. I'm going to write that in terms of A. So pressure of A times V equals the moles of A times RT. Now remember, R is the ideal gas constant, and in this case it would be 0.08206 liters, atmospheres, moles, Kelvin. So that means that we definitely need to work in temperature units of Kelvin. Pressures would be in atmospheres. However, you could convert that to torr or millimeters of mercury after you solve the problem. The volume is in liters. And then, of course, we have moles right here. Now, since the concentration of A is equal to the moles of A over V, you can look at the ideal gas law and rearrange it such that we see this term within it. So, P, partial pressure of A, is equal to moles of A RT over V. And so we see this here, and we see that there. And so therefore, this is equal to the concentration of A, RT. And now we're starting to see the relationship between the partial pressure of a gas and its concentration. You could rearrange this to solve for the concentration of A is equal to the partial pressure of A over RT. And I want to make this even more generic and just say the concentration of X is equal to Px over RT, because I want us to investigate a chemical reaction. So let's now consider AA plus BB gives us CC plus DD. Now, if I asked you to write the equilibrium constant expression in terms of concentration, it would be products over reactants, but you use the concentration terms in molarity. Now I can substitute the partial pressure of each gas over RT for each of these here. So I'll go ahead and do that. And I'm going to just simplify. I want to pull out the partial pressures as one term, and so I'm going to show you that. And also combine the 1 over RT terms here. And when you do that, so when we pull out these terms 1 over RT, 1 over RT, and combine them, because they were multiplied together, then we would add up their exponents. So this would be C plus D, and this would be A plus B. As you can imagine, we can simplify this even further as just 1 over RT, but when they're divided, then you subtract them. So this is what it would end up looking like. Minus A plus B. All right. And we have seen this expression before. This is essentially the Kp expression. So Kp times 1 over RT C plus D minus A plus B. So Kc is equal to Kp times 1 over RT to the C plus D minus A plus B power. And so you can see how we utilize the ideal gas law to illustrate the relationship between the partial pressure and the concentration of a gas. And then we utilize the equilibrium constant expression in terms of concentration, plugged in that relationship that we derived here, and then just simplified further, once again to illustrate the relationship between Kp and Kc. Well, we can simplify even more. Let's say that we represent that change here as change in moles, because essentially that's what it is. It's basically the number of moles of products minus the number of moles of the reactants. Then we can represent the relationship between Kc and Kp as such. So Kc is equal to Kp times 1 over RT to the change in N, or Kp, if you were to rearrange this equation, Kp is equal to Kc times RT to the change in N. And this is actually, this equation here is on your info sheet that I provide for your assessments. So make sure you feel comfortable taking this equation and then solving for Kc if a problem asks you to do so. Just rearrange it. Now, I said that Kc and Kp are generally not the same as one another, but there's a case when they are, when they can be equal to one another, and that's when the change in moles is equal to 0. If you have the same number of moles on both sides, because you can imagine anything to the 0 power is what? 1. So all this term would cancel out. All this term would cancel out too, and that's when Kp is equal to Kc. So that's the only scenario where that works out, okay? Now, something I also want to make note of is that the change in moles can be negative. I think a lot of times students feel very uncomfortable with this concept, and I remember feeling uncomfortable too when I was first learning it. A negative number of moles just seems to defeat, law of conservation of mass. But remember, this is just an algebra equation, and if you take the absolute value, then you won't get the right answer. So if you get a negative number of moles, just work past the uncomfortable feeling and use it as negative, and so therefore you will get the correct answer. And I'm going to show you an example problem, what I mean by that, okay? Remember that we do not include units for equilibrium constants, so it doesn't matter which one you're doing, Kp or Kc, just never include units for those. All right, so let's work a couple of examples together, because I think the big thing here is it's easy to plug and chug into these formulas, but I want to make sure you feel comfortable with calculating change of N and how to figure out where do you get these little numbers from. Just remember, these little numbers are just the stoichiometric coefficient. So you're not doing any dimensional analysis here and calculating moles for mass or anything like that. You're just simply looking at the balanced chemical equation. All right, so here we have dinitrogen tetraoxide to make nitrogen dioxide. Okay? And we see that it's balanced, so that's good. And we want to calculate Kp from the Kc, given that the temperature is 298 Kelvin. So first order of business, you want to calculate the change in moles. So change in moles is products minus reactants. So the number of moles of products is 2. The number of moles of reactants is 1. So 2 minus 1 is 1. Remember that I got that from the balanced chemical equation. So the dinitrogen tetraoxide has 1 in front of it. It's not necessarily written in there. All right, so 2 minus 1 is 1. And now we can plug and chug. So Kp is equal to Kc times RT to the change in N, 5.9 times 10 to the negative third, times 0.08206 times 298 whoopsie, to the first. And when you plug that into your calculator, you should get 0.14 as your final answer. Now, based on the KC and the KP, what does this say about this particular equilibrium equation? Does it favor products or does it favor reactants? Excellent. It favors reactants. When you have an equilibrium constant less than 1, then reactants are favored. Now, in this case here, having, in terms of partial pressures, it's not a whole lot less than 1 here. So there definitely will be some products left over, but it's, looking at the KC here, this definitely has a considerable amount more reactants than it does products. Okay. All right, so I suggest that you pause the video here and try to do this problem on your own to test yourself, and then come back and check your work with me. All right, so let's go ahead and get started. So we have nitrogen gas plus hydrogen gas to make ammonia. We have a Kc of 3.7 times 10 to the 8th. And so first order of business, calculate the number of moles. I do that by looking at the stoichiometric coefficients and do products minus reactants. So here I have 2 minus a 1 plus 3. Since there's 4 moles of reactants there, 2 minus 4 is -2. Keep it as a -2, don't change it. So now let's go ahead and put that into our formula. Kc RT to the delta N. So that is 3.7 times 10 to the 8th times 0.08206 times 298 to the -2. Also, practice plugging this into your calculator. A lot of times, especially if you have like a scientific calculator, if you don't put the parentheses where you should put the parentheses, you could get some weird answer. So first thing you want to do when you're plugging in your calculator is I just plug this term in first. I multiply this together and then I raise it to the -2. And then I take that answer and then I multiply it by the Kc. I find that when students plug it into the calculators, they just go left to right. And in doing so, the calculator will multiply this together and then maybe raise everything to the -2 or just raise 298 to the -2 and they get some weird, bizarre answer. So make sure you're thinking about your order of operation. Now, if you have a graphing calculator, it's a little bit easier to visualize this. But once again, I have a graphing calculator I like to use. I always kind of plug this in first, then raise that whole term to that power, and then finish off multiplying because I don't want this to do the whole thing and mess up my answer. So just a word of caution there. As someone who's experienced calculator errors, it's no fun, right? So 6.2 times 10 to the 5th would be the answer for Kp here. And does this favor products or does this one favor reactants? Excellent. This definitely favors products for sure. K is greater than 1. And for both Kp and Kc, they will always agree with one another in terms of it favors products or reactants here. And as you see here, that Kp is not equal to Kc. Same for the other one too. They're not equal to one another. So I'm hoping that this video helped to elucidate why that's the case through that derivation of the ideal gas law and the relationship between a partial pressure of a gas and its concentration, that Kp is not necessarily equal to Kc, and the only time it is is if the change in moles of products minus reactants ends up being 0. Thank you all for watching, and I will see you next time.